Welcome to another topic of statics. Today I'm going to concentrate on discussing moment of a force, cross product, moment of a force in the vector formulation, and the principle of moments. As such, our today's objective would be for you to be able to understand and define moment and determine moments of a force in 2D and 3D cases. Certain activities that are associated with this lecture are reading quiz, applications, moment in 2D and 3D. There will be concept quizzes. There would also be group problem solving and attention quiz at the end of today's recording. Let's concentrate on a reading quiz to test your knowledge at this stage, and the best way to do that is to actually provide these two little questions. What is the moment of the 10 Newton force about point A? That moment is called M sub A or MA, but it is important to know how to be able to calculate that, and toward the end of today's lecture you should be able to know that. The distance from point A, the vertical distance, the shortest distance between point A and the 10 Newton force that's given is shown here. So we like to find the moment of the 10 Newton force about point A. Okay. So the answer would be B, 12 times 3. Actually, this should be 12 instead of 10. I don't know why is it 10 here, but it actually is supposed to be 12. Anyways, the correction is made. So that is simply 12 times 3, and that is 36 Newton meter. Let's concentrate on the second problem here. And the second problem here is the moment of force F about point A is defined as M sub O. How do we define that? Use a cross product R times F. Again, this is just to warm you up. It's a reading quiz. Later on, you would be able to have a much better understanding of the concept that I just discussed. So this is just for you to make sure you guys complete your reading before we can actually start talking about the topic. So some of the applications of where we can actually calculate the moment, the applications are really endless. An example is given here. We have a beam here. In this case, beam is used here to bridge the gap in walls, and it might be over a window, or it could be under a window, what have you. In this case, or it could be for the roof of a building, and so on. So in this case, we would like to know what would be the effects of force F on the supports A and B. If the condition of the supports are known, then we may or may not have a force, a moment at A and D, and at A and B. In this case, the A is supposed to be is assumed to be fixed. As such, we are going to have a moment at point A that is simply a force multiplied by D sub A in this particular case. Again, we're just concentrating on the applications. Another common application, this would actually help those of you guys that have had difficulty pulling stubborn nails out of a board or a beam or what have you. Many times we try to hammer, we don't use the support at O, it makes it more difficult. But if you use a support, just a 2x4, and we just use that as the support, then it is much easier to pull out the stubborn nail. So how could we mathematically model the effect of force F sub H at point A, and who cares? Could be one of the questions in your mind. Well, we do care about this. In this case, it may be trivial to many of us, but think about much larger forces that are needed and much larger devices. In this case, we're talking about pulling a nail out of a board. It could be pulling much stronger, much bigger members out of the ground, or moving them around. Again, that's why we care about calculating that. Note that in this case, F sub H is actually the force that is exerted on the hammer by the arm, and that the arm of a person, and that is pretty perpendicular to the hammer itself. So let me move on by introduce you of a moment of a force in scalar form. In scalar form, the moment of a force about a point provides a measure of the tendency of rotation. That's also sometimes called a torque, not to be confusing torque and moment. They're different concepts, but the moment of a force about a point provides a measure of a tendency of rotation. In the two-dimensional case, the magnitude of the moment is simply, if we would like to have a magnitude of moment about point A, a tendency to rotate, a sense of rotation, and the force is applied counterclockwise. And in order for us to calculate the moment about point O, we simply find the shortest distance between O and the vector F in this case, and that is the perpendicular distance. In this case, it's going to be little d, so m sub O would be simply F times d. As shown, d is the perpendicular distance from point A to the line of action of the force, so something what I like to call sometimes the shortest distance. In 2D, the direction of m sub O is either clockwise or counterclockwise, depending on the tendency of the rotation. Now, another example that's shown here, vector F is acting in the direction that's shown. We would like to find the magnitude of moment about point O. In this case, it may not be as trivial. Again, we find the shortest distance between point O and vector F, which is a perpendicular line. We draw that, and as such, we can simply see that we can calculate m sub O as such. Note, in this case, we could also break F into the two components, F sub X and F sub Y. This typical sign convention is pretty much for moments in 2D. It's the this is if in this case we consider counterclockwise positive. I consider counterclockwise positive myself, but again, if we really don't consider the sign and we just be consistent with the sign convention that we use, the answers would turn out to be correct. But as you can see later when we solve the problems, I assume the counterclockwise positive. You can assume it either way, follow my sign convention, or in either case, if you stay consistent with your sign convention, all the moments for a problem counterclockwise positive, or all the moments counterclockwise is the positive direction, clockwise is the positive direction, the answers would turn out to be the same. So we can pretty much determine the direction of a rotation by imagining the body pinned at A and deciding which way the body would rotate because of the force. Again, each of us, we have different way of having that mental image, and it's important to realize that if this point O is fixed, for example, in this case, I'm showing that in red here, okay? If we apply the force F, vector F, in this case, it cannot be, if O is fixed, it really cannot go clockwise. So the only way the rotation that's caused by force F must be counterclockwise in this case. But again, with practice, you would do much better. So Finding a moment of a force in 2D in many cases is straightforward. However, there are cases in which they may not be as straightforward as we like it to be. It's not really that trivial, especially in three-dimensional space. As such, we are going to introduce to you a more general and more accurate approach in solving moment problems or calculating moments in space, in three-dimensional space, by using a cross product of the two vectors. It's more like a general. It involves vector operations. You've probably practiced this from your calculus using the right-hand rule. If you have two vectors A and B, and you would like to find a cross product of A cross B, you simply point your fingers from A to B using your right hand. The thumb would be pretty much pointing to the C direction, which would be the cross product of the direction of the cross product of A times B. Now, if there's an angle between A and B, then the cross product of A cross B would be simply AB, a sine of that angle. And of course, the unit vector U sub C, which is acting using the right-hand rule, is acting upward, as shown in this case. So C would be A cross B, is simply AB sine of theta U sub C. So here's another example. Again, the ij component in this case shown on the figure on the right-hand side, positive to the left and negative to the right, meaning that if we go from I to J, J to K, and then the cross product of I cross J would be positive, the cross product of J to K would be positive. But if we follow the other way around, if we go from example from K to J, and then the cross product would turn out to be negative. Also from J to I, it's going to be negative. From I to K, it would be negative, and so on. Again, with practice, we would know about that. If you do a cross product of a vector by itself, the answer would be 0. For example, a vector cross into itself, I cross I would be 0, J cross J would be 0, and K cross K would be 0. And as I just mentioned, if you follow this sign convention, multiplying I by J, it's going to be K. Multiplying K by I, it would be J. The other way around, multiplying K by J, well, not multiplying, crossing K by J, it is going to be negative I. Crossing J by I, it's going to be negative K. Crossing I by K, it would be negative J, and so on. So this is really what we use in cross producting two vectors. Also, the cross product could be written as a determinant of the matrix IJK. First line, it's a 3 by 3 matrix. IJK, that's the first line. Second line, A sub x, A sub y, A sub z. The third line, B sub x, B sub y, B sub z. And we take the determinant of this matrix, and that would give us A cross B. Do you remember how to do the determinant of such a matrix? We cross the first line, first column to the left out, and then we would say A sub y, B sub z, I minus A sub z, and B sub y, I. That's for the I component. For the J component, remember, we're taking the determinant, so the second term would be the negative sign. If you don't remember that from your calculus, we review it. We are reviewing it right now. The second, for the element J, we cross first line, second row out. We take the determinant by doing a simple multiplication of the A sub x by B sub z, again, minus, don't forget these minus signs, the way they appear here I put a check mark on top of them. And remember, every time you take the determinant, the first term is positive, the second one, there is a negative sign carried by the operation itself. For the k element, we cross this last column and last line out, a sub x b sub y minus a sub y b sub k. This is for I element, j element, and k element. So if you want to use the vector formulation of moment of a force, we can calculate it using, again, a 2D approach, but it can be difficult and time consuming. So it is often easier to use the vector cross product. Again, m, the vector that will be produced, moment of the axis m sub o about a point O. It is simply r cross f. And in this case, r is the position vector from point O to any point on the line of action of f. So please keep that in mind. Then the plane of ORF is shown here by white triangle. You can see that here. That is perpendicular to m sub O. Okay. So, using the cross product of the moment, then we can express m sub O as r multiplied by f. We set the matrix as such: ijk, r sub x, r sub y, r sub z. This is the first line would be the unit vector. The second line would be the components of r. The first component of the cross in this case, and the f would be the second component of the cross product, in this case f sub x, f sub y, f sub z. So by expanding the above equations using a 2x2 determinants as just the same way I just showed you, we get m sub o, again ijk, and we make sure we follow the plus and minus signs that are associated with the determinant, and that would give us the result of m sub o. Now the physical meaning of this equation is evident by considering the force component separately and using a 2D formulation. In 3D, it's not as easy, but again, the physical meaning is if we do that in 2D, then we are simply using the cross product and the angle that's involved, and in that case, it is much easier to be able to see what it really means to do that. So let's take a look at a quick example. As I am going through more slides, things would become more clear to you. It should become more clear to you. So I'm just trying to bring it to the right slide. There we go. So example number one, we are given a 100 Newton force in the way it's applied to the frame that's given. One side of the frame at point O is fixed to a wall. The length of the legs of this L-shaped frame is given. The angle in which the 100 Newton force is applied is also given in the form of 3, 4, 5 using similar triangles. These are common in mechanics. The way it's shown in engineering mechanics is commonly shown. We would like to find the moment of force at point A. What should be our plan? The plan should be to resolve 100 Newton along x and y axis and then take the moments separately. Again, in this case, we use a scalar analysis. For the two force components, we add them to simply get the moment. How do we do it? The solution, we take the summation of forces about y, we set that to 0. In the y direction, there is minus 100. 3/5 of that would be the, here's the x component. This is the y component. This is y. This is x. They are perpendicular. This is the vector. This is the direction of the components of x and y. So For the x direction, it will be 100 times 4/5 of that. Summation of moment about O. Both components of f sub x, namely f sub x and f sub y, would cause moment about point O. They both have a tendency to cause rotation at about point O. Also, your x and y coordinate system could be put here. Again, these are perpendicular. I butchered them, but the right way is to draw a straight line to the right of the page and straight line down to the page with a 90-degree angle. They are normal to each other. So as such, we would calculate that for the negative 100 Newton. We simply multiply that by 5. That would be the moment arm. However, for the x component, the line of action of the force would go through that. The distance would be, perpendicular distance would be 2 meters as shown. This is perpendicular, right? And that must be multiplied by 2. This was my crazy drawing here, and as such we add them up, and we also follow the sign convention. Again, we try to stay consistent. In this case, we assume the counterclockwise to be positive. Both of them turn out to be negative because they're both have a tendency to rotate that in a clockwise rotation. Now, if you assume that the sign convention, as clockwise positive, okay, as I show here, okay, if I assume that as to be positive, still, both of them would turn out to be negative, and the m sub O would be minus 460 Newton meter. Again, as we do more problems, things would become more clear to you. Let's do another example. Example number 2. Given the force and geometry shown, find a moment of F about point O. This is 3D. As you can see, in order to determine the direction of the moment, the magnitude of the moment about point O due to force that's shown acting at point B, things are not as trivial. So we need to do more than just looking at the problem, be able to tell what will be the direction of the force. This is 3D. So our plan should be to pretty much find R sub OB. Remember the cross product. And then we would determine M sub O by calculating R sub OA times F. You'll see that shortly. This is a great problem. So first we would find the position vector R sub OB. Remember, I've already defined that. Position vector R sub OB. Okay, so the R sub OB would determine the position of the force vector, the point in which the force vector is acting on with respect to the point that we would like to calculate the moment about. If they're the same, our job would be a whole lot easier. A whole lot easier. If it's not, then it's going to be a little bit more difficult. So 0I, since the I component, which is in the x direction, is 0, and there's only j and k component. The j component is 3, the k component is 1.5, and we can find the position vector as such, all of the components of that. So then we're going to find the moment by using the cross product. Remember the moment about point A, we simply put ijk. The second row would be the components of the position vector, 0, 3, 1.5, and the third row would be the components of the force that causes the vector by about point O, which is given here by the problem, minus 6, 3, and 10. This is the minus 6, this is 3, and 10, right? So minus 6, 3, and 10. So 3 times 10 minus 1.5. We take the determinant as I just described to you previously. The answer would be 25.5 I, 9J, plus 9J, plus 18K Newton meter. Let's take a look at a very interesting concept quiz. Both of them are very interesting. Now, if a force of magnitude F can be applied in 4 different 2D configurations. Look at all the different force configurations that are shown. S, R, Q, and P. Meaning that if you want to apply the force P, we can apply it upward, kind of upward, in this direction that's shown. Q could be perpendicular upward. R would be in an angle upward, and S would be to the bolt or what have we. It would be the line of action of force S was going to go through the bolt. Now, if we can do that, we would like to select the cases resulting in the maximum and minimum torque value on the knot. Again, principles of statics are shown to be everywhere so far, and as when you're done with this class, you would, I hope you would think everything and that are in static equilibrium in terms of statics equilibrium. Very important to do that. So, which one would be result in maximum and minimum torque values on the knot? That's which one is the maximum, which one is the minimum. S would be the minimum, right? So it cannot be A or C. We are looking for maximum and the minimum. So let's identify the minimum right away. S would cause the minimum because the line of action, again, it's supposed to be a straight line. It's going to go, the line of action of S is going to go through the bolt or not, what have you there, okay? So that would cause the minimum, okay? So it's either B or C. Now, which one would cause the maximum? Which one would be resulting in the maximum value for torque? And that is the perpendicular force that's applied at this point, which is Q. So the correct answer turned out to be D. Okay. Okay. Now let me ask you this: if we have a cross product, R cross F would turn out to be M, then what will be the value of M dot R? Again, that's also very interesting. If R cross F is M, what would be M dot R? Well, in this case, it's going to be a 0 because by definition of the cross product and dot product. Go back and review your dot product. This is a good opportunity to do so without me telling you why. Why don't you guys go back and review your dot product so this will also serve as a review for you. But the correct answer would be 0 in this case. Now let me continue by taking a look at a more complicated problem that's shown here before we can take a look at another problem. We're going to do 2 problems and then we would actually have another attention quiz and we would wrap things up. So let's take a look at this group problem solving problem. Given a 20-pound force is applied to the hammer, the moment of the force at A is unknown, and we would like to determine that. Again, it's a very smart way of pulling those stubborn nails out. Okay, so we know the force, 20 pounds. We would like to find the moment at A. Now, what should be our plan? I'm switching between 2 screens here that I have in front of me, and sometimes that confuses me. Anyways, the plan is, since this is a 2D problem, let's resolve the 20-pound force along the handles X and Y axis. We would determine M sub A using a scalar analysis. That would be our plan. So let's take a look at force F again. F sub y is applied again. X and y and components, x and y axis. The Cartesian coordinate system is given here, and as you can see, there will be 30-degree angle between x component or x-axis and F. As such, F sub y would be 20 sine 30, and F sub x would be 20 cosine 30. Please note that the arrows right next to F sub y and F sub x, that shows the positive direction of y and x. We also use the same thing for moment. As you can see here, this direction, counterclockwise, is assumed to be positive moment. And then we take the moment, very similar to one of the problems that we just did. For the x component and y component, they both cause moment. We simply consider their directions. Both are negative, and the 351.77, which is rounded to 352 pound-inch. Also, we want to make sure that we always express the sign of the resultant m. In this case, this is turned out to be negative, so this is going to be, remember, we assume a counterclockwise is positive, so this is going to be clockwise, okay? So make sure you guys follow this. Again, I cannot emphasize enough. Okay. All right, let's do a little problem that's more crazy. Group problem solving. The force and geometry shown. Moment of F about point O. What would be that moment? How do we solve a problem like that? Again, this is the one that requires a position vector, because simply the F1 that's shown here doesn't go through O. It goes through another point, and there's a distance between the point in which we would like to calculate the moment about and the point that the vector is really applied, indeed applied. In this case, O and A. Okay, so we need to find the position vector R sub OA that goes from O to A, and we simply cross that position vector by F and determine the moment about point O. So it's also important to realize here that this is R sub OA, not R sub AO, and that is because we would like to find the moment about point A. I'm sorry, moment about point O, and F is actually applied at A. Okay, let's get on with it. Solution R sub OA. Again, the IJK components. We are looking for a vector that goes from O to A. So the position of the A in space, the X component is 3, Y component is 5, the J component is 4. That's the distance. So I'll take that back. Actually, the distance of A in the X component is 4, Y component 5, and the J, which is in the Z direction, is 3. So 4I plus 5J plus 3K foot. Now let's take the determinant of the infamous matrix that we've been using so far. First row is a 3 by 3 matrix. First row is IJK. Second row is the position vector, OA, components of that, 4, 5, 3. Remember, I must be correspond to the second row must also be correspond to I, correspond to J, and correspond to K. So don't mix these up by shuffling them around. If you put 3 instead of under K, you put 3 here under the J component, I guarantee you, you're going to get the incorrect result. And the last row of this matrix would be the ij components of the vector itself. So it's going to be 100 minus 120 plus 75. We simply take the determinant of that to get the cross product. It's going to be turn out to be 735i plus 0j minus 980k. That would be the moment about 0.0. Let me take a look at an attention quiz now, and then we wrap up our session. As you can see, point P is given, and there are two vectors, 5n and 10n. The CCW direction, counterclockwise CCW direction as positive. So this is the positive direction, right? This is a plus, okay? Counterclockwise. Find the net moment of the two forces about point P. Net moment of two forces about point P. So this is not a couple. Two separate forces acting. So there will be a moment caused by the 10 Newton, positive, about point P. That's 10 times 3, 30. And there is also a negative moment. Again, I hope you get the sense of the direction. This one has a tendency to turn it in this way, clockwise, and the 10 Newton has a tendency to turn it counterclockwise, right? So 10 Newton meter, 20 Newton meter, minus 20 Newton meter, 40 Newton meter, and minus 40. So 10 times 3, 30, minus 10 would be 20. So the correct answer is 20 Newton meter. Next, if R is 5J meter and F is 10K Newton, the moment of R cross F, and what should that be? Remember, in the matrix IJ component, we're going to cross the I out in this case, and as you can see, we have a J component and a K component. So it obviously cannot be. Remember the rule of I, J, K, and the positive and negative direction that I just described to you. Go back to that slide and you can check that out. In this case, J would be multiplied by K. So the answer cannot be J, cannot be zero, and all we need to determine really is the sign of that. The J times K, again, the counterclockwise is positive, would turn out to be a positive number, so this is also out, and the correct answer would be 50I. That brings me to the end of what I wanted to cover today. That learning continue. If you have any questions, feel free to send them my way. Thank you.